AB Calculus Section 3.4, more rules on differentiation. This will be day number 1 of 3.4. Today specifically, we're going to discuss what's called the product and the quotient rules, as well as talk about the derivative of e to the kx. Okay, so pause the video right now, see as many of these derivatives as you can do by memory, and then come back and we'll talk about those that you do already know, as well as those that you don't. Okay, so I'm going to start here. Function f of x equals c. Of course, the derivative of a constant equals 0. It's called the constant rule. Derivative of f of x equals mx. That's linear. Therefore, the derivative function is the slope of the line. That's the linear rule. Derivative of f of x equals x squared is 2x. We would call that the quadratic rule. Cubic rule. Quartic rule. And then, of course, the general rule, which is called the power rule. Now, you may ask yourself, well, aren't all of these power rule? Yes, they are. Every one of these polynomials is considered a power rule. And for that matter, so is the constant rule. It's just a more specific example. So the power rule, the derivative of x to the nth, is n times x to the n minus 1th power. Okay, we talked about the sum and difference rule as well as e to the x. So I'm going to skip down here to e to the x. The derivative of h of x equals e to the x is e to the x. This is called the nice rule. That's a joke, but anytime you're working with e to the x, it's pretty nice. Okay, typically derivatives with e to the x are much easier to work with. The sum and difference rule, when taking the derivative of two functions that are added or subtracted together, you just take the derivative of each of them individually. So that'd be g prime of x plus or minus, depending on the situation, f prime of x. Okay, the product rule, which is the next one, is not quite so simple. Okay, the product rule, if you have the product of two functions, its derivative is the derivative of the first times the second left alone plus the derivative of the second times the first left alone. If you'd like to talk about the workings of how that's proven, please talk to me on the side and we can discuss. Or go on YouTube and type in proof of product rule calculus, and you'll see a number of videos on that. Okay, the quotient rule. Quotient, of course, is math term for divide. So if I've got a rational function, the derivative of h of x is going to be f of x, which is the lower function or the denominator, times the derivative of the upper function minus the upper function times the derivative of the lower function or the denominator divided by the denominator squared. Okay, so many times you might hear a teacher say low d high minus high d low over low squared. Okay, that's the quotient rule. You'll get plenty of practice with that, so that'll become second nature. Now, if you have a constant inside the exponent of e to the x, the derivative is still, I don't know why I put that over there, here we go, is still e to the kx, but then that constant comes out in front. And that's something, this is actually considered chain rule, but it's not the only way to do chain rule. So don't sit on that for too long and worry about understanding why. You're not going to see that much until future lessons. So let's continue with our rules here and do a few examples. Okay, example number 1. It looks like I've got the product of two functions. Therefore, I'm going to use the product rule, which says that I take the derivative of the first function. Derivative of the first function will be 3 multiply it by the second function left alone, then add that to the derivative of the second function, which is 2, times the first function left alone. Now you could leave your derivative just like that, or you could expand it and then combine like terms. That looks like it'll be 12x's minus 21 plus 10, which would be minus 11. Okay, provided I did my algebra right there, I think we should be, yeah, we're good there. Okay, so we use the product rule there. All right, number 2, I'm also going to use the product rule, but I'm going to rewrite the function in this form of two functions multiplied together. Okay, so the derivative of this function will be the derivative of the first with the second left alone, plus the derivative of the second, which is still going to be negative 5x, times the first one left alone. Okay, so this is unique because both functions are the same. There will be a better way to do this later. It'll actually be utilizing the chain rule, but we're not going to do that for now. So we should get 50x minus 80 for the derivative. Now, how did I get 50? Negative 5 times 5 is 25x. Same thing over here. I'm just going to double that to 50x. I get negative 40 and another negative 40, which makes negative 80. Okay, let's do another product rule in number 3. Number 3. Okay, so we're going to take the derivative of the first function, which will be 8x to the 7th minus e. Now notice, this is e times x, not e to the x. So this is a linear function with a slope of negative e. Okay, so this, continuing with the derivative, we'd get plus 6x times the second function left alone. And then we're going to add the derivative of the second function, which is negative 12x cubed times the first left alone. Now, you might be asking, okay, is he going to expand this whole thing? Nope, I'm not. I'm just going to leave it like that because I don't want to do all the expansion and combining of like terms. That's my choice. We will never, I shouldn't say that. We will likely not make you simplify because actually if you simplify and you get it wrong, your answer is incorrect. So this answer is correct, but if I were to simplify it or combine like terms incorrectly, then it would be incorrect. Okay, let's look at number 4. I'm going to change colors here. I need a change in scenery. Okay, this is going to be a quotient rule. So I'm going to use the quotient rule here because it is a rational function. Now I could use the product rule, but that would be getting into some kind of a mess here, so I'm not going to do that. Okay, so, but I'll show you that in future lessons. Okay, so we're going to take the low function, negative 3x to the 4th plus 2, times the derivative of the high function, which is 8x to the 7th, minus 1 plus 6x, minus, so this would be the low function times the derivative of the upper function, minus the upper function, trying to make space, times the derivative of the low function, which would be negative 12x cubed. Oh my gosh, I'm running out of space. Okay, that's all going to be over negative 3x to the 4th plus 2 quantity squared. There's your derivative. I am not cleaning that up, okay? But as you know, the low function, or the denominator, times the derivative of the upper, minus the upper function left alone times the derivative of the denominator over the denominator squared. Okay, let's keep moving. Different color. I like it. All right, looks like another quotient rule. So you can practice this on your own if you want to pause the video. I'm going to keep going. Denominator, derivative of the numerator, 27x to the 8th minus 2x plus 5 minus numerator left alone times the derivative of the denominator, 2x, all over denominator squared. Okay, no, I'm not simplifying that either. There's a lot of work there. Okay, let's look at Now, take this with a grain of salt. If we ask you to simplify fully, do it. Okay, and there will be scenarios where simplifying it fully is going to be important. However, right now, we're just trying to get the skills down. So learn the skills of product, quotient, and power. Okay, let's look at number 6. This is going to be a product rule. The first function is x. The second function is e to the 5x. So dy dx, okay, notice the difference in my notation, is going to be the derivative of the first, which will be 1, times the second left alone, plus the first times the derivative of the second. So that'd be e to the 5x times 5. Notice how that constant comes out. All right, so I'm going to regroup this just slightly because I want to make it look nice. This will be e to the 5x plus 5x e to the 5x. There's the derivative of y with respect to x. Okay, let's look at number 7. Find the equation of the tangent line to f of x at the point 3, 2. So I'm going to use point slope form. So I need a point, which I have, and I need a slope. I need to know this. What's f prime at 3? So I got to find f prime of x first. So I'm going to take the low function, x squared minus 1, times the derivative of the high, which is 2x, minus the upper function, x squared plus 1, times the derivative of the low, which is 2x, all over the denominator squared. Okay, so I could choose to clean this up if I wanted to, or I could input a 3 like right now, and I'm just going to input the 3. So that would be 3 squared, which is 9 minus 1, times 2 times 3, which is 6, minus 3 squared, which is 9 plus 1, times 2 times 6, or 2 times 3, which is 6 again, over 3 squared, which is 9, minus 1, squared. So let's clean this up a little bit. That'll be 8 times 6, which is 48, minus 10 times 6, which is 60, over 8 squared, which is 64. So the slope of f of x, of the tangent line at x equals 3, is going to be negative 12 64ths. I think we can probably clean that up a little bit and simplify. You could leave it right like that if you're afraid you might simplify incorrectly. But that would be negative 3/16. So I get a slope of negative 3/16 of the tangent line. Therefore, the equation of the tangent line would be y minus 2 is equal to negative 3/16 x minus 3. Now, I prefer point slope form because you can use any point. If you use slope intercept form, you can only use what's called the y-intercept. That's the only point you can use, 0, comma b, right? M being the slope, b being the y-coordinate of the y-intercept. Okay, let's continue on in the next slide. All right, example 8 says, what is the slope of the line tangent to the graph of y at x equals 1? So I want to know y prime at 1. Let's find y prime. At this point, you should start to feel comfortable with the quotient rule in this case. I'm going to take the low function, x plus 1, times the derivative of the upper function, which will be e to the negative x times negative 1. Okay, be careful with that. That's that chain rule coming into play, minus the upper function times the derivative of the low. So the derivative of the lower function is 1, the upper function is e to the negative x, all over the denominator squared. All right, so I'm going to plug in a 1. That'll give me negative 2e to the negative 1 minus e to the negative 1 over, and if I plug a 1 in the denominator, that'll be 2 squared, which is 4. Okay, I don't see that here, so I'm going to kind of clean this up. This looks like we get y prime at 1 would equal negative 3e to the negative 1s divided by 4. Now at this point, you could probably just by process of elimination, see that the answer is B, although that's not in the correct form yet. But I know that e to the negative 1 power is the same as 1 over e, so that would be negative 3 over 4e. That's the slope of the tangent line to that graph at x equals 1. All right, number 9. The function f is defined as the following. What points, x, y, so possibly multiple, on the graph of f have the property that the line tangent to that point, or points, is 1/2. So I want to know for what values of x is this true? Right? I want to know the values for x such that the derivative, or the slope of the tangent line, is 1/2. So let's work through it by first finding f prime of x. So f prime of x is low times the derivative of the upper, which is 1, minus upper times the derivative of the lower, which is also 1, over low squared. Okay, so I want to know where this is equal to 1/2. Well, if I combine like terms here, I say I'll get x minus x. That reduces. So I'm going to get 1/2 is equal to 2 over x plus 2 quantity squared. Now, you might already have the inclination to say, well, this expression has to equal 4. And you're right, because if 1 is to 2, as 2 is to something, then that something has to be 4. That goes right back to proportions in geometry. So I know that 4 has to equal x plus 2 quantity squared, which means 4 equals x squared plus 4x plus 4, which means that 0 equals x squared plus 4x. All right, so I'm just solving by factoring. And it looks like in order for this to be 0, either x equals 0 or x plus 4 equals 0. Therefore, x equals 0 or x equals negative 4. Okay, it doesn't look like I have to do a whole lot of work here. My only option is going to be C. But I could confirm, right, if I plugged in a 0, f of 0 would be 0 over 2. So f of 0 would be 0. And f of negative 4 would equal negative 4 over negative 4 plus 2. So f of negative 4 would equal negative 4 over negative 2, which would equal 2. Therefore, I can see those two ordered pairs show up. You may have to get to that point, especially if, for example, part D had a negative symbol there. You'd have to decipher then which of those two outputs, 2 or 2/3, would be present. Okay, let's continue. All right, example 10. Let f be a function defined by the following: k times the square root of x minus natural log of x for x greater than 0, where k is a positive constant. Find the first and the second derivative. Okay, so this is not just a hint, it's actually very important to this problem. But the derivative of f of x, first I'm going to write k square root of x is k x to the 1/2 minus the natural log of x. Okay, so the derivative of k square root of x is k over 2 x to the negative 1/2. And the derivative of negative ln of x is negative 1 over x. All right, I'm just going to actually rewrite that in a form that will be helpful here. That'll be k over 2 x to the negative 1/2 minus x to the negative 1. Now I've got everything in power rule form. So the second derivative directly off of that will equal negative k over 4 x to the negative 3/2. I subtracted 1 from negative 1/2. And then for negative x to the negative 1, that'll be a positive 1 x to the negative 2. So this would be acceptable for the second derivative, as well as these being acceptable equations for the first derivative. So the first derivative is good in either of those cases. This would be an acceptable second derivative, other than the fact that this plus looks like a arrow pointing down. But I would actually probably clean this up. It'll be easier to work with if you have to evaluate the second derivative. This would be negative k over 4x to the 3/2 plus 1 over x squared. That's my preference for how to write that, just because I know that at times you'll have to evaluate and it'll be easier in that form. Okay, let's look at example 11. Let h be a function defined for all x not equal to 0, such that h of 4 equals negative 3, and the derivative of h is given by h prime. Write an equation for the line tangent to the graph of h at x equals 4. Again, anytime you're asked to write an equation for a tangent line, you need a point, which we have, 4, negative 3, and you need a slope. I need to know what h prime at 4 is equal to. So I've got h prime of x. I'm just going to plug a 4 in. So it'll be 4 squared minus 2 over 4. This is a pretty quick and painless problem. That'll be 16 minus 2, which is 14 over 4. So we would say that the slope of the tangent line here is 7/2. So the equation of the tangent line for h is going to be y minus a negative 3 is equal to 7/2 x minus 4. There you have it. Okay, we got one more slide. Let's get to it. Okay, last example for today. It looks like we're going to pull in some continuity material here, as well as look at some derivative stuff. So first off, let's see if you remember what the derivative with respect to x of sine x is. We briefly spoke about it last lesson. The derivative of sine x is cosine x, and the derivative with respect to x of cosine x is negative sine x. Okay, those are coming down the pipe, so just be ready for them. Okay, so let f be the function defined by f of x, piecewise style, is equal to 1 minus 2 sine x for x less than or equal to 0, and e to the negative 4x for x greater than 0. Show that f is continuous at x equals 0. So the first step to continuity is to show that f of 0 exists. Well, f of 0 would equal 1 minus 2 sine of 0. And I knew that f of 0 was located there because I can see that this portion of the function includes 0. Okay, so what would f of 0 evaluate to? Well, f of 0 would then be 1 minus sine of 0 is 0, so 2 times 0 is also 0. So f of 0 equals 1. It exists. Perfect. Step 2, let's show that the limit exists as x approaches 0. So let's take the limit as x approaches 0 from the left of f of x. Well, we actually just calculated that. Okay, we calculated that in this step. And the reason why is because as x approaches 0 from the left, it is on this portion of the function. So I can say very confidently that the limit as x approaches 0 from the left of f of x is also 0. The limit as x approaches 0 from the right of f of x is going to be e to the negative 4 times 0, which is equal to, whoa, I goofed something up here. Wow, I did good maths. I wrote 0 when I should have wrote 1. Good. Okay, so this limit here, the limit coming from the right of 0 of f of x, is going to also be 1 because e to the 0 is 1. Therefore, step 2 is good. We can say then that the limit as x approaches 0 of f of x exists and it equals 1. Now, step 3 in continuity checklist is to show that f of 0 is equal to the limit as x approaches 0 of f of x, which it is. Okay, so we can say, based on the continuity checklist, that f of x is continuous at x equals 1. Now, it did say show that, so we already knew that was going to happen. Okay, let's look at part B. Part B says, for x not equal to 0, express f prime as a piecewise defined function. Okay, so f prime of x will be equal to the derivative of each of the two parts. So the derivative of 1 is 0, and the derivative of negative 2 times sine x is negative 2 cosine x. Okay, so that would be f prime on that interval, now only where x is less than 0. It tells us to exclude 0, so we're going to do that, but we'll talk more about that later. Okay, so we get negative 2 cosine x when x is less than 0. Okay, on the other portion of the piecewise, we're going to take the derivative of e to the negative 4x. Well, that's going to be negative 4 e to the negative 4x. And that's going to be for all values x greater than 0. So we've now defined f prime as a piecewise function. Our next step within this process is to find the value of x for which f prime is equal to negative 3. So what I want to do is I want to find the value coming from the left on the derivative. I want to find the x value such that this is true, if any exist. And the same thing coming from the right. I have to consider both functions and see if either the two sides of the piecewise take on a slope of negative 3. Okay, so I'm going to use negative 2 cosine x coming from the left, set it equal to negative 3, and on the other side, negative 4 e to the negative 4x, and set that equal to negative 3. Now let's solve. Let's start on the left side. Cosine x equals 3 halves. This is not going to exist. Why is that? Because the cosine graph maxes out at 1 and bottoms out at negative 1. All right, so there, from 0 to pi, we were not going to have a value above 1 or less than negative 1. Therefore, cosine cannot equal 1.5. You kidding me? Okay, now we're going to solve on the other side. Divide by negative 4. I get 3/4. I'm going to get an answer here, and the reason why is because I know that an exponential function that looks like this will equal 3/4 at some point. Let's figure out what that value will be. The best way to do this is to put this into logarithmic form. So here is our base. So our base of our log is e, which makes it a natural log. We take the natural log of 3/4 and we set it equal to the exponent. And then, of course, we're going to divide by negative 4. So the negative 1/4, the natural log of 3/4 is equal to x. Therefore, I could say that f prime of negative 1/4 ln of 3/4 gross is going to equal negative 3. There you have it, guys. That is 3.4, day number 1, quotient rule, product rule, a little bit of chain rule, and then, of course, a little bit of trig stuff too. All right, we'll see you in the next video.